Welcome to our Industrial Product Coatings Q&A. I'm OC. I'll be moderating this session. Our two presenters today are Bryce Anton, VaporTech Director of Technology, and David Wayne, our Commercial Business Director. For the next 30 minutes, Bryce and David will answer your pre-submitted questions. We will contact you to answer any questions that were pre-submitted but not addressed, and any questions asked in the chat. Let's get started.
All right, thanks, OC. Hello, everyone. Again, my name is David Wayne. I'm the Commercial Business Director here, and just going to get us started. First off, thank you, everyone, for the questions that you submitted. We've taken those, and a lot of them were in regards to similar topics. So we've combined those into a handful of topics here that I'm going to have Bryce speak to. And the first of those was really several folks were interested in the basics of PVD, or just a little bit of background on the PVD technology before we get into some of the more in-depth questions. So Bryce, I'll hand that over to you.
Thank you very much. Good afternoon, everybody. Glad you could all join today. And for those who are watching it after the fact, happy to be talking about these topics. Yeah, so the question about what is PVD, what is the technology behind how we apply the coatings? So PVD is an acronym, of course. It stands for physical vapor deposition. And I'll talk a little bit more about that technology of why we call it that. But generally be aware that it's a way of depositing thin film coatings, typically metallic-based coatings. We can deposit pure metals, just straight metals, or more commonly, especially on the industrial and functional side, we react those coatings with things like nitrogen to form nitrides, carbon gases to form carbides. We can do oxycarbides, carbonitrides, oxides. You name it. We have a lot of flexibility to do different types of reacted films that form coatings that are much harder, much more durable, and have enhanced properties than just a basic pure metal might have. So it gives us a lot of ways to solve problems, different ways to approach depending on what your application is in need of to solve a surface problem. So by physical vapor deposition, I mean that we're starting with something physical, meaning a metal target material. Usually a metal, like for example, titanium or zirconium. We start with a metal. We're going to remove atoms of that metal by some kind of energy, and we do this in a vacuum. We do this in a vacuum for a number of reasons, mostly to be able to control energy, to control reactions, and the plasma processes that we use to evaporate or remove material require low pressures to be stable. So material starts in a solid form, it gets evaporated, and it becomes a vapor. It translates through the vacuum until it condenses and lands on the parts. And the parts are typically loaded on some type of a rack or tooling that's inside the chamber that's custom designed to hold those parts so that we orient them in the best position so that they can get good coating coverage and whatnot. So these coatings grow atom by atom, but it's a quick process. A typical coating process can take anywhere from an hour to maybe a few hours, depending on how thick the coating needs to be applied. But it is still what we call an atomic deposition process. So keep
Bryce,
that in mind.
How thick would those coatings typically be for these type of applications?
Typically anywhere from a micron in thickness up to about 5 microns. And that thickness is ultimately depending on the need, what problem you're trying to solve. Typically, we try not to go any thicker than we need to because that's time, that's money. That's throughput. So during our coating development process, we try to optimize the thickness for the need of that application. So we have a couple different techniques that we use to evaporate or remove the material from the target. And these are the most common technologies used in industrial coatings, and they're cathodic arc evaporation and sputtering. And they're both plasma processes, but they have very different characteristics. And we'll talk a little bit more about when we use one over the other, but there are some advantages and disadvantages to both. But it usually has to do with the amount of energy and the amount of ionization that occurs. Cathodic arc evaporation is a highly energetic, high degree of ionization process. It's the most common used for industrial hard coatings because you can build the densest coatings. You have the most control over reactions if you're trying to form different types of compounds. But it does have a drawback in that there are droplets, and sometimes it's not the most defect-free coating. And that's where sputtering comes into play. And sputtering is more defect-free, it's lower energy, kind of a gentler process. But you can also get very hard, very durable coatings with sputtering as well. So that's one of the things that we look at as we're looking at a new application is what's the best fit for the need, whether it's maybe temperature control, maybe it's the smoothness, maybe it's the density. And so we'll go into more of that, but just be aware that there's more than just one way of growing a coating. And we use the two most common.
That kind of leads us into the next question, which was really around selecting the right coating for a particular application. And we had a number of questions that were related to different applications, but asked Bryce just to address some of the things that we look at in trying to pick that correct coating for a particular application.
Exactly. I mean, we could talk all day about this one, but we'll try and keep it a little bit general for this talk. But typically we run into three situations when we have a new opportunity come to us, and one is somebody's already got a product that's being coated, and maybe it's being done at a job shop or a service provider, and they're just looking to bring it in house, and they already know what coating works. And maybe it works or maybe it's not as good as they'd like it to be, but we at least have a starting point, and we can replicate that coating or make it better or do something different. Another situation is that it's an established application that people have been doing for a long time, and so we already know what works good for those types of applications, whether it's a cutting tool or a forming tool. There's really these coatings have been used for decades, so there's a really wealth of known coatings that work for certain applications. So we always have a good starting point. But where it gets really exciting, where we have the most fun from a coating development standpoint, is a new application, something that somebody's never done before. And that's where we really need to understand what are the requirements of the application, what's the environment that the coating is going to be used on, what's the material of the substrate, and what's it going to be interacting with. Is it something that's going to be a sliding wear application where we need a very lubricious coating? Is it something very high impact where we need to have something really tough? And so really trying to understand those applications and what the environment is. And these types of applications, just some examples of the most common ones we come across, or from tooling we get cutting tools, punches, plastic injection molds, die casting, things where you need release properties, where if you just use your bare metal, maybe it'll stick to it too much. And so these coatings can provide some of those attributes. Just making things last longer, that's really the name of the game. Function better and last longer. Surgical instruments we work quite a bit in, and it was some biocompatible coatings, so some of our titanium nitrides and such, our DLC coatings that we know are really well suitable for those industries. And then, of course, components like in automotive engines where you need tough coatings that are seeing impact, like for intake exhaust valves, or bearings where you need sliding and they need to be compatible with the types of lubrication used. And then implants, again, that biocompatibility. So these are things that we run into all the time. And the more we understand environment that it's put in, the limitations. Some substrates or some materials that need to be coated have temperature limitations. They're hardened steels. They can't get above a certain temperature. So we may need to choose a certain technology over another one if we need to manage thermal requirements, or what temperature is going to be used at. Does it need to be a higher temperature material? Do we need to make something that's going to resist oxidation? Is it something that that coating may have a corrosion situation where the environment is very difficult? So we always have to kind of get in there and understand where that's going to be used. And we've got a whole list of different coatings that we have really established properties that we can jump in there and work to. And so let's talk about just materials in general. So we do have a repertoire of coatings that we use, and they basically, for the most part, our industrial coatings, they usually start with a metal, and we have kind of our 5 main ones. We've got zirconium, titanium, chromium, tungsten, aluminum. These are the main ones that we deal with. And we can also make alloys of these coatings. For example, titanium aluminum or titanium aluminum chromium. We can mix and match either by making alloy targets or having multiple source materials just being deposited at the same time. And then we'll react these with different gases. And these are very common industrial gases, environmentally friendly, things like nitrogen and oxygen, basic gases, methane, acetylene for doing carbon gases. We try to avoid any of the more, noxious gases, complex gases, expensive gases. But, one of the things that, I really try to reinforce is trying to keep things as simple as possible. Things in the world are complicated enough. Let's not make the coatings more complicated than they need to be. So keep it as simple as possible when you're trying to develop a solution for a customer. So there's a lot of complex coatings out there, and there's always good reasons for it. Whether just trying to get it, that 10% better than something else, multi-layer coatings, different complex structures. They all have their place, but we always try to stay as simple as we can, because that just makes production and problem solving all the better. So,
Bryce, one question: if in a particular application, if a customer has a coating that exists already, is it possible to reverse engineer, or how would you go about that?
Oh, absolutely. That's very, very commonplace. Typically we will get a sample of that coating, and we can reverse engineer using our laboratory techniques. We've got glow discharge optical emission spectroscopy. We've got a scanning electron microscope with EDS. And so we can pretty quickly determine what that coating is comprised of, the different layers, the materials used, and then we can replicate it. We do that all the time. It's pretty regular occurrence in our business. So it's, we have the means to be able to measure, the coating hardness, the thickness, any of those attributes that we'll want to then go and match. It's a good question.
All right. Moving on to the next one. We just spoke there a lot about metal-based PVD finishes, and we had a few questions asking about DLC or diamond-like carbon, and how does that differ from what we just talked about?
Absolutely. DLC coatings are really exciting. There's a lot of great functionality that we can get from DLC coatings, but just the one thing to be clear is that the word DLC is used a lot. It basically just means diamond-like carbon. So these are carbon-based coatings that have some level of diamond-like properties, meaning the bonding of diamond is part of that makeup. They're usually a mixture of different bondings, and often they're hydrogenated, so they're never quite like pure diamond. But that's okay, because you actually don't necessarily want pure diamond hardness in most of your applications, because that would be much too brittle. So we like to have different ways of doing DLC coatings, and typically it's done most often by what we call plasma enhanced or plasma assisted chemical vapor deposition, which PECVD or PACVD. And typically what that is a plasma that we immerse the parts to be coated in. We backfill the chamber with a carbon-based gas, typically acetylene or sometimes methane or some other carbon gases. And that plasma will break down that gas molecule. It'll break it down, and as that material condenses on the part, you will just start to grow these carbon-based films. And depending on the temperatures, depending on the energy levels used, you can control the level of hardness and tailor some of the properties. You could dope those coatings with other types of gases like silicon-containing gases or nitrogen, or you can even do co-deposition with metals like tungsten. Tungsten DLCs are a very common one where you sputter from a tungsten target while you are depositing your diamond coating at the same time, and you get this really nice kind of a composite type coating where you've got this nice tungsten carbide matrix with a lubricious diamond structure, so you get these nice durable, tough, and lubricious coatings. So there's a wide range. Just long story short, there's a wide range of DLC coatings. They typically have very low friction, which is one of the reasons it's very popular. So really good on sliding wear. They're biocompatible. They tend to be very inert. They don't like to react with things too much. And so in a lot of those environments, it's very beneficial. So we use them in automotive components and medical devices, forming tools, you name it. And on top of that, it also looks really good. So we tend to use it a lot for decorative coatings, for jewelry, for luxury goods. It's for sporting goods. It's a very attractive coating. So, and also, what's better than putting diamond on your product, right? We often, another thing just to point out is we often combine our DLC coatings with our PVD coatings. I mentioned the tungsten, incorporating the tungsten in with the DLC, but we also tend to use a lot of adhesion layers or structured layers. Like, for example, we may use a metal like zirconium or chromium. Chromium nitride is a very common base for then applying our DLC on top. Chrome nitride is an extremely tough, durable coating, and it sticks to a wide range of different substrates. So we'll start off by applying a nice functional layer of chromium nitride, and then we'll apply the DLC at the top layer, which is just going to give it that additional lubricity that maybe the chrome nitride by itself doesn't have. So we do these engineered, tailored coatings where we optimize the properties, and we have the means to be able to do these different types of multi-layers and multi-structured coatings on a very regular basis. It's very common in our industry, and it's commonly done here at VaporTech.
I think it's also important, I think you alluded to this, Bryce, is that in most cases, the DLC processes can be run on the same piece of equipment.
Oh, yeah.
You're running metal processes in.
Absolutely. And that's how we've designed our systems, so that we have that capability of that flexibility. So, you can do a run of a chrome nitride or a titanium nitride hard coating, and then do a switch over, and then you can run your DLC coatings. It's done on a regular basis by a number of our customers, and we do it here while we run samples all the time. So it's pretty common. That's how we designed our systems, to be flexible in that way.
Yeah. Moving on to the next question, kind of along those lines, is for folks that don't have experience working with PVD equipment or applying the coatings, or maybe sending product out for coating at a service provider or the like, don't have a lot of experience with what that equipment actually looks like and what goes into it. And so we had some questions around just what does that equipment look like, and what's necessary to be able to apply any of these coatings.
Absolutely. So kind of the basics of a PVD chamber is a big vacuum chamber that you put your parts into, and then you have your targets, which are the starting material, the raw material, like we talked about before, whether it's the titanium or the tungsten. And there's different configurations of systems. VaporTech's been producing PVD systems for 40 years, and we've had different configurations. Some of our systems we have a target in the center of the chamber that spray outwards, but our newest product that we're launching right now has those targets on the outside. And this is a top-down view of what that looks like. And this is a system, it's kind of an octagonal shaped system with 2 clamshell doors that open on the sides. And there's 6 wall-mounted sources on the outside. And those sources they can be any type of deposition source. They could be cathodic arc sources, they could be sputtering sources, you name it. That gives you the flexibility to do multiple materials, multiple coating technologies. You could do sputtering and arc at the same time, or you could just do arc, and you can have one of your targets be titanium, your other target be chromium, or your other target be aluminum, and make these different mixtures of materials. So multiple deposition sources for multiple materials, and being able to do those different technologies at the same time or sequentially, or you do one batch of one type of technology and you do your next batch. Just by changing a recipe, you can do an entirely different technology altogether. These systems for the industrial coatings tend to be higher temperatures than, say, decorative coatings. We'll talk a little bit about that. But typically over 400 degrees is very common, especially for the sputtered coatings and some of the really high durability requirements for arc deposited coatings. But we can run anywhere in that range. And again, like I said, sometimes we have to run lower temperatures depending on the part sensitivity to temperature. And sometimes if the parts can take it, we'll get them real nice and hot, which only enhances the adhesive strength and the durability of the coating. So this is our VMAX 1500. Like I mentioned, this is being launched currently. This is what it looks like from the outside. You've got the picture you see here. It's got the chamber itself on the left-hand side, the blue box. All of the controls, the water distribution, the power distribution, the HMI, the PLC, it's all on the left-hand side in the gray box. It's all touchscreen controlled system. We're using turbomolecular pumps on this system. It's also equipped with a independent plasma source. There is a plasma source that we use for gas phase etching, as well as using it for the PECVD of the DLC. And it can also be used for metal nitriding, which is another way to enhance the toughness and the durability of the substrate prior to building up the hard coating. One of the things that's really important on the functional side, well, actually important for any kind of coating deposition, but is the pretreatment, making sure that the coating is being applied on a nice, clean, fresh surface that's well prepared. And so we do that with temperature, and we also do that with etching, plasma treatments prior to depositing the coatings. Really, really important for building those really tough, durable coatings. So this is a nice compact system. It's all built on a single skid, ease of moving it around the plant and transporting it. We do have a removable turntable that has either 6 or 12 spindles of parts. We can also do triple axis rotation if you've got a lot of small parts that need independent rotation. Otherwise, it'd be 2-axis rotation. So really, part rotation can be actually 1, 2, or 3-axis rotation, and with a removable table. So really flexible system. Really excited to see how we could work with a lot of new applications.
All right. And then for the last question, we had, while our focus here was really on industrial coatings, we did have a number of questions that were around color. And I think it's important to note color coatings, industrial coatings in many cases are the same thing. They may be made of a lot of the same materials. And so we had questions just around color availability, uniformity, and then also a second question just around cathodic arc and sputtering. specifically for deco?
Sure. Yeah, so VaporTech has worked in the world of decorative coatings for our entire existence, and it's actually what we're most known for. Although we've worked with functional hard coatings in about equal amounts over our years, but typically these types of industries that use these coatings are door hardware, plumbing fixtures, sporting goods, firearms, automotives have always been a big area for us, jewelry, consumer electronics. We make a wide range of colors, and I think we've probably got the most extensive portfolio of decorative coatings out there on the market. We kind of break our coatings down into a couple different categories, whether they're opaque coatings or optical coatings. The opaque coatings is we're typically trying to replicate natural looking coatings like your golds, your bronzes, your silvers, your stainless steel colors, really trying to match natural looking alloy colors, but with these enhanced properties of the durability, corrosion resistance that you'd expect from a hard coating. And then we also have our range of optical coatings, which, sort of the blacker coatings, the more unnatural coatings, you might say, blue coatings, and some of our graphitic anthracite type colors where they may not be as natural in nature or as common in nature, but we use optical effects in how we build those coatings. So there's a lot of different ways that we can build these coatings and design these coatings, and whether we're trying to match an existing finish or come up with a brand new color, that's kind of our bread and butter. So cathodic arc and magnetron sputtering are both used for decorative coatings. Traditionally, cathodic arc has been the more common technique used, mostly because of that high energy that you get, high ionization from the nature of that energetic process. You can control reactions a lot easier at lower temperatures. So we can do our decorative coatings on plastic parts, very common that you see in plumbing products, electroplated, hand showers, veggie sprayers, or internal automotive components that are ABS plastic. So we can control those reactions to form those compounds, those carbonitrides, carbides, nitrides, with the energy of the ions rather than having to apply thermal energy. Now, if you're doing it with sputtering, you may need to add more thermal energy to get those reactions to occur. So it's usually not as common. There's always exceptions, but not as common for plastic components. We do have a new black process that we've been under development with for the last few years that we've launched last year that is a sputtered black chromium carbide. It's beautiful. It can be made at low temperatures. It's really a fantastic process, and it's made by sputtering. The material is very similar to what we do for our functional coatings. Titanium and zirconium. Zirconium is the most common, but titanium, zirconium, chromium, those are the three we use most often for those types of coatings. Again, they can be used for either magnetron sputtering or cathodic arc. Composition tends to be a little easier to control with our cathodic arc because that ionization, and the uniformity has a little bit better throw because of that energy level as well. But application-wise, it really depends on what color you're trying to achieve, what type of substrate you're trying to apply it to. But we have certain coatings that tend to work, or colors that work better with sputtering, some that work better with cathodic arc, some we can do with both. So it really is a conversation about trying to understand what's the end use, what are the properties needed, what's the material you need to apply the coating on, and then we can direct into the right technology.
All right. Thanks, Bryce. I'm just going to hand this back over to OC now that we're finishing up.
Thanks. And thanks to everybody here. So here's our contact information. Please do contact us to continue this conversation. Before we go, I'm excited to share that VaporTech is celebrating 30 years as a Masco company, alongside sister companies like Delta Faucet and Behr Paint, and that our systems are designed and assembled here in the United States. And we offer sales and service from our locations in Europe and Asia. Have a great rest of your day.
Thanks, everyone. We appreciate your
everybody.
time.